Hello again. In the last unit, you tackled some pretty tough stuff. So I thought we'd do something easy today. Let's learn to count. Ready? 1, 2, 3. Okay, maybe not that easy. Today, we are going to count the number of atoms in this sample of copper, the number of formula units in this sample of salt, and the number of molecules in this sample of water. In order to understand how to count them, you are going to have to meet and understand the mole.
In this lesson, you will define the term mole, calculate molar masses, calculate the number of atoms, molecules, or formula units in a sample when given the mass of the sample, and calculate the mass of a sample when given the number of atoms, molecules, or formula units in the sample.
Oh, I was just trying to see the atoms in our sample of copper, but I'm having trouble. How are we going to count them if we can't see them? We have learned enough chemistry to know that atoms exist, but they are just so darn tiny. Even though atoms can't be seen, they are very real to a chemist. So real that chemists have developed a system for counting atoms. I know that seems pretty bizarre. I mean, the question still remains, how can you count something you can't even see? Let's do a little experiment to try to find out.
The students have been given a cup with 3 dozen grains of rice. They find the mass of the rice to be 0.58 grams. This means that the rice has a mass of 0.19 grams per dozen grains of rice. To check this, the students are now going to find the mass of 6 dozen grains of rice. The mass is 1.24 grams, which gives a mass of 0.21 grams per dozen grains of rice. Allowing for experimental error, the two calculations are the same. Now the students find the mass of a sample of an unknown amount. The mass is 1.94 grams.
So, using the conversion factor that the mass is 0.21 grams per dozen grains of rice, I want you to calculate how many grains of rice are in the sample of rice that has a mass of 1.94 grams. Did you get it? You should have figured out that there are approximately 9 dozen grains of rice in this sample. Remember, when you work a conversion problem, you let the units guide you. So, we put 0.21 grams on bottom and 1 dozen grains of rice on top. We multiply and get 9.2 dozen grains of rice. Let's peek back in on the students to check our answer.
The students are counting the grains of rice in the sample. They have divided the sample into piles with a dozen grains of rice in each. They have 1, 2, 3, 4, 5, 6, 7, 8, 9 dozen, with 2 grains of rice left over.
Excellent. The students were able to use mass to count the number of grains of rice in the sample. They could count the number of grains of rice in this bag without even opening the bag. Are you thinking what I'm thinking? Perhaps we can calculate the number of atoms in our sample of copper, the number of formula units in our sample of salt, and the number of molecules in our sample of water without having to actually see them and count them. Of course we can. Chemists are the smartest of people, after all. And they have come up with a system for counting atoms. Pretty impressive. Think about the experiment our students performed. They didn't try to work with a single grain of rice because grains of rice are so small. They worked with dozens of grains of rice. And we all know that a dozen is just 12. Since an atom is so much smaller than a grain of rice, trying to work with dozens isn't going to help us here. chemists have come up with a number that is used to help with the counting of very tiny atoms. It is the mole.
A mole is simply a number, a very large number. Sometimes this number is called Avogadro's number in honor of Amedeo Avogadro, who was the first to propose the concept of the mole. A mole is equal to 6.02 times 10 to the 23rd power. Just like a dozen is always equal to 12, a mole is always equal to 6.02 times 10 to the 23rd power.
So, if you have a dozen donut holes, you have 12 donut holes. And if you have a mole of donut holes, you have 6.02 times 10 to the 23rd power donut holes. Now that's a lot of donut holes. In fact, if you covered the surface of the Earth with a mole of donut holes, they would be 5 miles deep. A mole really is a huge number. In fact, it is so large that our brains have trouble comprehending it. So, why talk about a mole? What's the point? Well, the mole is a very important number in the world of chemistry. After all, it is going to give us a way to count atoms that we can't come close to seeing. Let's see how.
To understand counting atoms using the mole, we will compare oxygen and sulfur. First of all, think about this. We know that 1 mole of oxygen atoms is 6.02 times 10 to the 23rd atoms, and 1 mole of sulfur atoms is 6.02 times 10 to the 23rd atoms. So they have the same number of atoms. Would they have the same mass?
We must consult the periodic table for the answer to this question. The atomic mass of sulfur is approximately 32 atomic mass units, and the atomic mass of oxygen is approximately 16 atomic mass units. So, a sulfur atom is twice as heavy as an oxygen atom, and a mole of sulfur atoms would be twice as heavy as a mole of oxygen atoms. That doesn't seem to help us with the counting, but those very smart chemists picked 6.02 times 10 to the 23rd for a good reason. This number of sulfur atoms has a mass of 32 grams, and this number of oxygen atoms has a mass of 16 grams. In fact, you can look at any element on the periodic table, and the atomic mass will tell you the mass in grams for a mole of that element's atoms. Pretty neat, huh? Aren't those chemists something?
The mass of 1 mole of pure substance is known as its molar mass. The molar mass of an element in grams per mole is equal to the atomic mass for that element. The molar mass of a compound is equal to the sum of the molar masses of the elements making up the compound.
Before we use molar mass to count, let's practice finding the molar mass of both elements and compounds. Use your periodic table to find the molar mass of magnesium and chlorine. Easy, huh? The molar mass of magnesium is 24.3 grams per mole, and the molar mass of chlorine is 35.5 grams per mole. Remember, the molar mass is the mass of 1 mole, so the units are grams per mole. Now, let's try something a little harder. What is the molar mass of magnesium chloride? We're going to need to know the formula for magnesium chloride to find the molar mass. Magnesium has a charge of positive 2, and chlorine has a charge of negative 1. We crisscross the charges and get a formula of MgCl2. I told you that it was going to be very important that you mastered formula writing. I wasn't kidding. If you are still having trouble with this, get help. Get help now before you dig yourself a hole that will be very difficult to climb out of. Check with your local teacher for a convenient time to come in and get some extra help. That being said, let's get back to our problem. To find the molar mass of magnesium chloride, we will add up the molar masses of magnesium and chlorine. Except, look at the formula. Each formula unit of magnesium chloride has 1 magnesium atom and 2 chlorine atoms. So, we need to multiply the molar mass of chlorine by 2 before we add them. Now we add 24.3 grams per mole plus 71.0 grams per mole equals 95.3 grams per mole. Now it's your turn.
Find the molar mass of aluminum oxide. Now check your work. The formula for aluminum oxide is Al2O3. Its molar mass is 102.0 grams per mole.